wait, wrong. Yeah, that's correct. Yeah. So let's go through the solutions of the three problems. Yeah, so let's look at the first problem. So basically, yeah, so there are N cows that are being interviewed for a position, and each one has a competency score CI ranging from 1 to C inclusive. And you're given the values of CI, and some of them are equal to 0, which means that they haven't been assigned yet. And you're also given Q pairs, AJ to HJ. And basically what this means is that if you consider the prefix max from 1 to HJ, then, sorry, 1 to AJ, then HJ is the first place that's greater than the prefix max. And it's basically asking you to fill in the zeros that's lexicographically smallest that satisfies all these AJ, HJ constraints. And yeah, just a remark. Yeah, so I think this problem is definitely the trickiest one this contest, but let's go through the problem. Yeah, so one thing you can think about is, so basically for each AJ, HJ pair, you can consider the interval AJ plus 1 to HJ. So just consider like all these kinds of LR intervals that are of the form AJ plus 1 to HJ. And let's try to see what kinds of properties they have. So what we know about an interval is basically if we consider the prefix max M, all these elements have to be less than or equal to M, and then this has to be strictly greater than M. This is because this is the first element that is strictly greater than the prefix max. So let's try looking at some properties of these intervals. So let's say that the intervals intersect. So if they share the same right endpoint, then basically we have that if this is the prefix max, then yeah, uh, yeah. So basically, this is the first element. If this is M1 and this is M2, this is the first element that's greater than M2, and this is the first element that's greater than M1. But since we have this interval here, all of these elements have to be less than or equal to M1. So this tells you that if you have two intervals that share the same right endpoint, then we can just eliminate this interval and just take the bigger one. So one thing is if intervals share right endpoint, take the bigger one. And let's consider another case in which the intervals intersect. So let's say I have two intervals that intersect and they don't have the same right endpoints, right? So if this is a prefix maximum M, then this is the first element here that's greater than M, and all of these elements are less than or equal to M. So this tells you that this element is less than or equal to M. And then, so let's just say this is M2, like this prefix, yeah. So prefix max here is is M2, which is less than or equal to M. And this is the first element that's greater than M2. But that's a contradiction, right? Because this here was supposed to be the first element that was greater than M2. So basically, you're not allowed to have intersections like this. So basically, uh, if right endpoints are different, then there's no solution. So because of property 2, that means that all of the intervals, they're only allowed to share the right endpoint. And because of property 1, we can always take the longest interval. So this basically tells us that we can assume the intervals are disjoint. So now let's look at what we can say given the intervals are disjoint. Yeah, just a reminder, each interval represents like aj plus 1 to hj. Yeah, so let's just consider disjoint intervals, right? And basically we can consider going from left to right. And then this has to be greater than the prefix max here. And this has to be less than or equal to the prefix max here. But we know that this, since it's the right endpoint of an interval, this is the greatest element within its prefix. So we can actually reduce the problem to this size, right? And what we can do is some of these values will equal 0. And we can greedily change some of them. We can greedily change them to 1s. And then, yeah, and then you'll have like some non-zeros in your input already. So this might be like 2, 3, 5, 7 or something. And this has to be greater than 7, right? So one thing that you need to have is that this is the first element that is greater than everything else to the left, right? So basically, all these all these elements have to be greater than or equal to the second largest in this range, right? So if there exists an element in this range that's greater than or equal to the second largest in this range, then we're done. Otherwise, since we want to find the lexicographically smallest, you have to look left to the closest 0 and then change this to be the second largest. Yeah, so just to repeat, since this is the first element, since this is the first element that's greater than this prefix max, then that means everything to the left, or the prefix max of the left should be at least the second largest in the interval. So if there's no element here that's at least the second largest, then we have to replace some element with some element that's at least the second largest. And since we're looking for lexicographically smallest, we pick the closest 0 to the left and replace it with the second largest. And since this is the largest in its prefix, then we don't care about any of the elements to the left. So we're only reducing the problem to this region in red. Yeah. And then we'll set this thing equal to, if it's not already set, you can set this equal to max. So if this is L and this is R, then you can set this equal to max C from 1 to R minus 1 plus 1. Since this has to be greater than everything to its left. But if there's a 0, and let's say that there's no zeros here, and we're processing the next interval, and we want to replace a 0 to the left with a second maximum. So we also have to add some kind of, we also consider this as a candidate for the 0. And if this is not as large as the second maximum, then you can consider this as a candidate to increment to the second largest. Yeah, so that's essentially the idea. So let me summarize this, or let me summarize the idea. So basically we can reduce the problem to something where the intervals are all disjoint, and then we can process the intervals one by one. And within each interval, you can greedily set the zeros equal to 1. And we must have, we argued earlier that we must have that the prefix max to the left must be at least the second largest element. And since we want the lexicographically smallest, you find the closest 0 to your left and change that to the second smallest. And then you change this to max plus 1. And if it's if it's a 0, you can still consider it as a candidate for an element to change when you're looking at the next interval. And then at the end, just change all the zeros to ones and then check if it's valid. Yeah. So that's the idea for solution to problem 1. Yeah, so there's a lot of greedy arguments that are made in this. And I think reducing the problem to just focus on this range from the rightmost endpoint of the previous interval to the rightmost endpoint of the current interval is important. Yeah. Any questions? Yeah, and you can like during implementation, you might want to pre-compute things like closest 0 to the left an element. Yeah, and then uh just process these kinds of ranges in blocks one by one and solve for each block. Yeah. Yeah, I'll move on to the next problem.